In our first example, we have the third root of 27, z to the ninth. This is the first time that we've simplified radicals when we have variables involved. So I want to show you a couple different strategies for how to do this. First thing that you would do basically, and you're going to get to a point where you don't actually have to show this step, but this is the third root of 27 times the third root of z to the ninth. Third root of 27, we're used to that. Take a look at your perfects chart. What is the third root of 27? Three. Now, if it wasn't in your perfects chart, you already know how to simplify a radical. If it had been the cube root of 54, you'd be able to break it up into the cube root of 27 times the cube root of 2. You'd be able to simplify that part of the radical. Now the letter part. There's a couple different ways to think about this. So I'm going to write in 3 different ways, and I'll let you decide which method you prefer, which method you want to write down. One way is to think about the fact that a third root cancels out a perfect cube. So if I can rewrite z to the ninth as perfect cubes, I can cancel out the radical. So this is the cube root of z to the third times the cube root of z to the third times the cube root of z to the third. 3 and 3 and 3 is 9. So all 9 of my z's are accounted for. I just grouped them into groups of 3. The cube root of z to the third is z. The cube root of z to the third is z. The cube root of z to the third is z. How many z's do I have no longer under the radical? 3 of them. So we have 3z cubed. Okay, the next way to think about this is what I do for my Algebra B class, and they really like it, and I think you'll understand why here in a minute. Instead of writing it out like that, I ask them to write it out as the cube root of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is a cube root prison. These z's are sitting in a cube root prison. And the only way to break out of a cube root prison is to have a group of 3 people. Groups of 3 can break out. Any less than 3, they can't break out. So here's a group of 3 that can break out and become a normal z. Here's a group of 3 that can break out and become a normal z. And here's a group of 3 that can break out and become a normal z. So they actually write it all out and physically look for groups of 3. So if that analogy works for you and you think about, all right, we've got 9 z's, how many groups of 3 can break out, how many would be left over, use that method. The more mathematical way to think about this is the cube root of z to the ninth is z to the 9 thirds. Remember, the index of the radical is the denominator of the fraction. What is 9 divided by 3? 3. So this becomes z to the third. The time that this doesn't quite work perfectly, what if we had the cube root of z to the 10th? That would be z to the 10 thirds. Well, 10 thirds doesn't become a whole number, but we do know that if you do 10 divided by 3, it is 3 remainder 1. There's 1 left over. So if you think about this in terms of dividing the exponent divided by the index and then looking at remainders. But ultimately this one simplifies to 3z to the third. And as we're going through here, I'll try to talk through as many methods for doing this as absolutely possible. Number 2 is honestly the exact same kind of problem, but it's written with rational exponents. So remember that an exponent of 1/2 is the same as a square root. So this is the square root of 16g to the 4th, h to the 2nd. Okay, what is the square root of 16? 4. What is the square root of g to the 4th? We have 4 g's hanging out under the radical. Because this is a square root, you need groups of 2 to get out. So how many groups of 2 do you have in 4? 2 full groups of 2. Or think about doing 4 divided by 2, and that gives you 2. The square root of h squared is plain old ordinary h. So our simplified answer is 4g squared h. And technically, because this came from an even index, we should put a plus minus in front of it. We're getting to the point now where this is complicated enough. If you don't put the plus minus in, it's not that big of a deal, but it's always good to put a plus minus when you're dealing with an even index. I was going to have you try number 3 on your own, but I changed my mind. We are going to do number 3 together. So, third root of 8. Let's start with the third root of 8. Look at your perfects chart. What is the third root of 8? 2. Third root of r to the third. R to the third is a full 3. That's a full group of 3. So that becomes plain r. Okay. The cube root of s to the 5th. We're talking about s to the 5th. That's 5 factors of s. 5 divided by 3. How many groups of 3 are in 5? 1 full group, so that's a plain s. How many are then left over? If you take those 3 out of the 5, how many are left over? 2. So we have the cube root of s squared. Those 2 are left stuck under the radical. So s to the 5th inside the radical became s times the cube root of s squared. Now let's try to simplify our t to the 10th. We have the cube root of t to the 10th. If you have 10 factors of t, how many groups of 3 are inside 10? 3 groups of 3. That would take out 9 of them. So 3 groups, oops, this is t, not s. 3 full groups are able to come out, leaving 1 left over. Okay? Think of it as 10 divided by 3 is 3, remainder 1. The remainder is what's left under the radical. This is why we teach you about division with remainders. Do you remember, like, putting beans or counters or something on your desk? And so 10 divided by 3, you break it into 3 groups of 3, and then there's that 1 left over. Do you remember doing that with, like, manipulatives in elementary school? Some of you? You've completely blocked out elementary school? Okay, cool. Now, how do we write this as a cohesive answer? Your answer needs to be numbers and letters in alphabetical order that are not under the radical, and then 1 radical symbol, numbers and letters that are still under the radical. So the 2rs t cubed, that's going to be written first. And then we write a cube root of the stuff that's still under the radical, s squared t. Now that may not look simpler than what we started with, but a simplified radical by definition is an nth root that no longer has any perfect nth terms under it. So if it's a cube root, we can't have any perfect cubes left under the radical. We have to pull all the perfect cubes out and cancel out the radical. I would like you to try number 4 on your own after we get it started. What is an exponent of 1/4 the same as? A 4th root. This is the 4th root of 625, j to the 8th, k to the 4th. Okay, the 4th root of 625. What is the 4th root of 625? 5. What is the 4th root of j to the 8th? We have j. If you've got 8 factors of j under the radical, how many groups of 4 are inside 8? two groups of 4, so j squared is how it simplifies. K to the 4th, if you got 4 factors of k, that's one group of 4, so we have k. So our answer is 5j squared k. Now for this one, would you have had to change it into the 4th root? You don't necessarily have to. You could do 625 to the 1/4. Know that that's the 4th root of 625, which is 5. And then for these, you'd multiply the exponents. 8 times 1/4 is 2. 4 times 1/4 is 1. So you can do this without transferring to a radical. But if there's remainders, it's almost easier in radical form. All right, take a look at number 5. Number 5 is actually pretty easy. On the top, the 5th root of x to the 5th. What is the 5th root of x to the 5th going to be? X. The 5th root and the exponent of 5 cancel each other out. On the bottom, the 5th root of y to the 10th. Y squared. Okay? You've got 10 factors of y. How many groups of 5? 2 groups of 5. Number 6, however, there are going to be some remainders. So, on the top, the 4th root of x to the 8th. How many groups of 4 are in x to the 8th? 2 groups. So that's going to be x squared on the top of our fraction. Okay, y to the 11th. How many groups of 4 are in 11? 2. That would take up 8 of them. And if we took 8 of these 11 out, how many would be left over? 3. So we still have the 4th root of y to the 3rd. Some of you might benefit from doing this. 4th root of y to the 11th. Split it into the 4th root of y to the 8th and the 4th root of y to the 3rd. 4th root of y to the 8th. 8 divided by 4 is 2, so we know this is plain y squared. And then you have the 4th root of y to the 3rd left over. So if you need to step over to the side and do some side work, that is okay. Your math does not have to be perfect from beginning to end. You can have little side pieces all over if you need to. On the bottom, the 4th root of z to the 6th. We can split that into the 4th root of z to the 4th, and then the leftover 2 factors. 4 and 2 add up to 6. The 4th root of z to the 4th is z. So we have z times the 4th root of z squared. Does anybody see a problem with this answer? There's a radical on the bottom. Can we have a radical on the bottom? No. Now, I honestly think that rationalizing denominators with letters is easier than rationalizing denominators with numbers. Because to make this radical go away, how many factors of z do we need under the radical? To make a 4th root go away, we need z to the 4th. We currently have z squared. How many more z's do we need? 2 more z's. So we are going to multiply by the 4th root of z squared on the bottom and the top. On the top, we have x squared, y squared, the 4th root of y to the 3rd, z squared. On the bottom, we have a z, and what just happened here? We completed the group of 4. So now we have the 4th root of z to the 4th. This becomes a plain old ordinary z. So how many factors of z do we now have on the bottom? Z squared.